Okay, I thought that today we would return to the rocketry problem and look at the example of a one-dimensional, meaning vertical rocket that's being launched in a uniform gravitational field. And what we mean here is we're assuming that the acceleration due to gravity is a constant, so we're not going too high up. And we are accounting for the fact that the mass of the rocket is changing. So it's not like that previous problem that had a generic constant thrust. Actually, this does have a constant thrust, but the mass in that previous example was maintained. Here, the mass is changing with time. And we're going to recall some things that we learned from our last case, which is generically, by using conservation of momentum, we were able to write down basically a formula for the thrust force that's due to the changing mass of a system. So this thrust force here was minus the exhaust speed times the rate at which the mass is being ejected. And so what we mean by this is U here is how quickly the exhaust is coming out relative to the rocket, and dm dt is the rate of change of the rocket's mass. I'm going to assume that that's a constant here, so it's ejecting mass at a constant rate, some number of kilograms per second. Of course, it's a negative number because the mass of the rocket is decreasing as it sheds mass. I'll just call that B. And then if we're ignoring everything like drag, we'll come back to that later, let's just say that the only other force that's acting on the rocket, of course, would be the downwards gravitational force, which depends on its instantaneous mass. And then this will give us the acceleration in the vertical direction. Okay, so our goals here are fourfold. We got a lot to do. First, I want to find what is the speed of the rocket as a function of time, assuming it launches from rest on the ground. I also want to know what is its position, its height as a function of time, how high does it go, and how long is it in the air? So these are a lot of various questions. We will have to kind of break down its motion sometimes into before and after its burnout time, things like that. So let's start by looking at that. The first thing we want to recognize here, let me rewrite our equation of motion once. So we've got the second derivative of y. I'll divide everything through by m. Notice that the minus sign here and the minus sign here, I'll just go ahead and rewrite that as b, cancel out. So I do have a positive upwards thrust. That's good. So that'll be ub divided by m. Now, we didn't say it over here, but we actually do know what m is. M as a function of time is whatever the initial rocket launch, initial rocket mass is, minus bt. So I could, if desired, put in m naught minus bt as my m when I divide through, and then I'll also have this minus g hanging off the end. Notice the mass cancels from that term. The very first thing we should recognize here is that, well, initially, the thrust needs to be large enough to actually get it to lift off the ground. So we'll just note that over here. At time 0, we need to have this greater than 0. UB over the initial mass has to be greater than or equal to g. In other words, if the thrust, and that's a combination of these two terms, so either the speed of the exhaust is not high enough, or the mass ejection rate is not high enough, or it's just too dang heavy, is not larger than g, then the rocket's just going to sit there on the launch pad burning fuel until it's light enough that this does overcome g, and then it'll lift off. So the very first thing we need to have any sort of interesting dynamics at all is to assume that the rocket's not too heavy, or that there's enough thrust to get it off the ground. So we're going to make this assumption for liftoff. Okay, now we want to integrate this once to find the velocity. I'm going to also assume that this starts at rest. Most rockets do start at rest on the Earth. So my integration constant won't be anything to worry about. And then I see that I just have a direct integral that I can do. It's a function of time directly. So I'll just integrate this from 0 up to some generic time t. And that's dt. I'll do this second piece first, because this is exactly what you would expect if this was just a ballistics projectile, so no thrust. You'd have the velocity is just going to be minus gt. And if it's on the ground, that'll just be 0. or if it's dropped, this would be its velocity. And then this term, because I've got a t in the denominator, I will end up with a natural log. So let's see what we'll have. The ub will come to the front. I am going to have a natural log of this stuff evaluated from 0 to t, and then I just got to make sure I've got the chain rule appropriate here. If I take this derivative, I'm going to pick up a negative b, so I'm going to actually divide this by negative b. And that will ensure that when I take this derivative, I'll end up with the appropriate units. The b's cancel. However, well, we'll see what happens. So I'm going to do a minus u. This natural log, I do have to plug in both limits. And don't forget that the difference of logs is the log of a quotient. So I'll have m naught minus bt over m naught. And then like before, it's convenient for us to flip this by getting rid of the negative. And so I'll write this as u log m naught over m naught minus bt minus gt. All right, so that is my velocity as a function of time. So that's nice. I got that one. Next, we're going to want to figure out what the position as a function of time is. By the way, just a couple things to note here. The units check out. That's always a good thing to check. So this u has units of exhaust speed, so that'll work. We can see that when t equals 0, that's gone, and I get a log of 1, so it starts at rest. That's good. We are expecting this, again, needs to have this sort of condition so that this actually has a positive speed. It will if that condition is satisfied. But notice that we've got a couple things working against us here. First, this negative t is going to gradually slow things down if all else was kept the same. As this t gets bigger, this denominator is going to get smaller, which is going to make this log bigger, but only logarithmically. So remember that although this term will actually get larger and larger with time, I mean, it does speed up as the thrust continues to burn, it's only growing logarithmically, and this is sort of growing linearly in time. So eventually this thing is going to stop. Okay, next let's find y. So we're going to integrate this one more time. Very similar integral. I'm going to assume that it starts at y equals 0. So y is just going to be the time integral, again, from 0 to t of this chunk. I'll do the second piece first just because it's so familiar to us. There's that minus 1/2 gt squared we always see. And then for this next piece, well, this one's maybe a little trickier, so let's do a little side calculation. I need to know what the integral of log is. So let's just figure out how we can do the integral of log x. Many of you probably already know this. This screams out for integration by parts. In fact, usually when we're doing a integral of an inverse function, like a logarithm or an inverse trig function or something, integration by parts is very useful. And I want to let my u variable equal that inverse function. Here, there's nothing else to write home about, so my v will just be x, and my du, of course, will be dx over x. But the reason we like this is because I can then use integration by parts. I'm going to have x ln x minus the integral of, well, v du. But of course, that's just going to be, these x's cancel, that's the integral of dx. So I get x ln x minus x. That's the general form of this particular integral. And so over here, it's probably useful for us to rewrite this whole thing as x, just to make life a little easier. And actually, I'm going to do one more thing. Let's actually flip this to make it minus u, just so we don't have to do any weird chain rule, quotient rule stuff. And I'm going to make the substitution x equals all of this stuff inside, which means dx is minus b over m naught dt. And then I really do have a negative log x. So my integral, I'll put a plus, well, I guess the minus sign now, right? I'll do a minus u, I'll have an integral, we'll change it in a sec. Natural log of x, that's good, because that's what I have up here. My dt is going to pick up a minus m naught over b dx, And then I can plug in my bounds right now too. So when t equals 0, x is equal to 1. And when t is equal to t, well, x is all of this stuff. All over m naught. And now we can use the result that we just did down below. This minus and this minus will combine. I can pull that constant out to the front. And then I'm going to have x ln x minus x, not 1, evaluated from 1 to this mess. Okay, let's go ahead and plug everything in. So we've got this minus 1/2 gt squared. We've got this mu naught over b. Funny that that happens to have units of distance, but such is life. When I plug in 1, the natural log of 1 is going to give me a 0. And I'm going to have a minus 1, but it's in the lower bound, so that'll give me a plus 1. I'm actually doing the lower bound first here. And then for the upper bound, well, I am going to have to plug everything in. So I have m naught minus bt over m, natural log m naught minus bt over m, and then minus m naught minus bt over m. Sorry, all of these should be m naughts. Now, there are several other ways that you could write this down. For example, I could just leave m naught minus bt as m of t. This should also be an m naught. All these m's should be m naughts. Okay. I also could divide this out and have this minus 1 and this plus 1 cancel each other and have a minus minus with a linear term. Maybe I'll do that too. And then just because I like writing positive numbers first, I'll do that. So I'll have bt over m naught, and then this piece here. As usual, I do kind of prefer to write this with a minus sign. So we'll have minus m naught minus bt over m naught, and then the log of this reciprocal. It's personal preference, I guess. And that's y of t. Okay, so we have y of t. And of course, I'm realizing I forgot my quadratic term here. Minus 1/2 gt squared. All important. Okay. Like I said, there are a few other ways you could write this. You could distribute this term and see that you have a u times t. So that's our sort of linear term that you would expect if you had a constant exhaust velocity and nothing else going on. The quadratic term we get from gravity, but the new bit is this logarithmic term. And actually, it's log linear. It multiplies by a linear function out front. Okay, so this is my height as a function of time. We found our velocity already. Now we're ready to start looking at some specific values. So first off, I might want to know how high does this go? Now we are going to have to break that into a couple pieces because initially the rocket is going to have thrust as it's accelerating upwards. Then it's going to burn out all of its fuel and move under ballistic motion until it reaches its true apex. So maybe I don't want to write down the whole height because I would have to add on that extra piece. And it's not hard to do, but it's just an extra term that we've already done a million times. How high does a projectile go? But let's go ahead and find out how high it is when the rocket exhausts its fuel. So to do that, we're going to have to introduce something called the burnout time. So notice that the burnout time, which is usually called TB or something like that, is the time that makes the mass go to 0, or at least to some final mass that is not going to have fuel anymore. We could imagine modeling our rocket as basically very, very light, where all of its mass is fuel. If you don't like that, fine. We can just subtract over. It's going to be the initial mass, that's the fuselage plus all of its fuel, minus the mass, the final mass, okay, this F is not fuel, it's final, or fuselage if you want, divided by the mass ejection rate. So this is the burnout time. After this time, it's no longer going to have any thrust. The thrust goes to zero. You don't suddenly have like a negative mass or something. That would be nonsense. So let's go ahead and summarize some of these things, and we'll try to use this burnout time to find what the height is when it reaches that time. Okay, a little summary. So here's our burnout time. Tells us how long until the rocket runs out of fuel. After that, it'll be in ballistic motion. This was just the launch condition, so we had to make sure that you actually had enough thrust to get off the ground in the first place. We're going to be implicitly assuming that really everywhere here, but just wanted to throw that up there. Here's our velocity as a function of time starting from rest. Notice it's got this logarithmic time dependence and then a linear piece. Here's the position as a function of time. I went ahead and distributed and did a little bit of rewriting. So we've got the exhaust velocity times t, a linear piece, our usual quadratic piece from gravity, and then this weird logarithmic term. I went ahead and wrote m as just m of t instead of this m naught minus bt, just to keep things a little more condensed. But it does have that logarithm of the initial mass over the mass at time t. Now, we're going to calculate the height kind of two ways. First, we need to find the height at burnout. So this is the height that the rocket has when it runs out of fuel. That's just going to be y evaluated at this specific time. So I'm just going to plug that in. TB goes here, TB goes here. Notice that here I can replace my m's with just m final, because that's the definition of the burnout time. At the burnout time, the mass is just the final mass or the fuselage mass or the frame mass, whatever F you want, but not fuel, not fuel. This is it. That is the height that the rocket has at burnout. But it's also moving at that time, and so it'll continue to rise until gravity has finally turned it back over. And so my final maximal height is going to be the height at burnout plus the initial, or the extra v squared over 2g that I would get, where v is the speed of the rocket at burnout. So now I got to go plug this in. I'll just write this as h. It's the thing that's just above it. And then this v term will be, well, I'll write a 1 over 2g, and then we've got u log m naught over just m. I'm not going to bother writing out the full thing, minus gt, and then that's quantity squared. Squaring this out does actually have a few simplifying things, because, for example, when I square this, I'm going to get a g squared t squared over 2g. That's a positive 1/2 gt squared, which will exactly cancel, oh, sorry, this t is t burnout. That'll exactly cancel the 1/2 gt burnout squared that I have in the original bit. So that's one simplification. What else might happen? Let's see. When I cross multiply here, I'll get a u log stuff times this t burnout over g. And then up here, when I go plug in my t burnout, there will be a term that also has this final mass in it. At any rate, the algebra is a little annoying. It doesn't simplify terribly. Let me give you what the final form is simplified. Okay, so here it is when everything's written out. We can see that that first term does survive. The quadratic terms do cancel away like I promised. It does turn out that the linear terms in logarithms do combine to give you, they don't cancel, but they do give you a single value that depends only on m naught. And then because of the square here, we do end up with a log squared term that depends on that exhaust velocity squared. So if you write it this way, it does actually kind of simplify. This, of course, was mf. A little bit. You could, if you want, go plug in a few more of these parameters, but I think this is about as clean as we want. So this is a little interesting. Your maximal height depends on the square of the log of the initial and final mass. Notice that comes with a positive sign. This one, though, comes with a negative sign, so it is partly offset by a stronger function, right? Log squared grows a lot slower. Well, I guess no, it doesn't grow slower. It's not log, it's log squared. So this term does win out in the end. You do get a positive value here, but again, everything is only logarithmically dependent on these masses. Okay, so that gives us our height. The last thing we might be interested in is the time of flight. Now, that one also has to be done in pieces. And unfortunately, this one doesn't really simplify as much as even this one did. So I won't write all the pieces out, but we can enumerate them. First of all, there's the time to get up to where the rocket runs out of fuel. So there's the burn time. Got to add that in first. Then there's a time I'll call T1, which is the time it takes for the rocket to reach its apex. So how long is that? Well, I know that during that bit, the acceleration is just minus g, and it comes to a rest at the apex. So this term is just going to be what? V at TB, that's the speed that it has at burnout, divided by g. Okay, so we could go plug that in, and it is what that is. Finally, there is the remaining time, T2, which is the fall time from the apex all the way back down to the ground. Now, for that, we'll use kinematics also and recognize that, oh, well, this is just going to be square root of 2g over h. 2h over g. Where h really is this whole thing. So the stages of the rocket, we have launch at t equals 0 with some initial acceleration, no initial velocity though. It rises until TB. At that point, the engine's cut off, so this is the burnout. Then it ballistically continues to rise. This time difference right here is what I'm calling T1. And then it'll turn over and fall back to Earth, and that time is what I'm calling T2. This height is, of course, y equals capital H, and this is y equals lowercase h. Again, because taking the square root of this thing is nasty, and because plugging in v of TB here is also nasty, there's not much simplification, I hate to say it. I guess you get one tiny bit here, which is that this minus gt times TB and this TB do actually cancel. So there's like that little bit. You are left with the logarithmic term out front, and then you're left with this messy square root that does not simplify. At any rate, we do have an expression, though, for the total time that it's in the air, or individual pieces of time if we need that. So I think that is a pretty good analysis of the one-dimensional rocket with constant gravity. Of course, you can imagine where you might go with this. We could start adding in a drag force. We could start looking at two-dimensional motion where we've got horizontal components of our velocity. We could also start looking at gravity that's not uniform. We're building our way towards the Kepler problem, but for now, I think this is a pretty good analysis of at least the second simplest case after the free particle rocket. Okay, there's our analysis, and we'll see where we go from here. QED.